Scattered through the ancient concrete of Roman harbor walls are small white mineral chunks that researchers once dismissed as evidence of sloppy mixing, and those same imperfections turn out to be the reason the walls are still standing in the sea today. Beneath the surface of the Tyrrhenian Sea, off the coast of what was once the Roman port of Portus, there are piers of concrete that have been standing in saltwater for more than 2,000 years, and they are still standing now. The light that reaches them is dim and filtered, the color of old glass shifting with the movement of water above. Sediment has settled into every crevice over the centuries, and small marine organisms have made their homes in the surfaces. But the structures themselves have not dissolved, have not crumbled away in layers, have not been eaten through from the inside out. They simply persist, the way old mountains persist, with a kind of patience that has no particular relationship to effort. Portus was the great harbour built to serve Rome, constructed at the mouth of the Tiber River where it opens toward the sea, and its piers and breakwaters were built directly into open water, laid in place while the sea moved around the workers, the material hardening in the presence of the very element it was meant to hold back. The harbour handled an enormous volume of shipping in its time, grain and oil and timber and stone arriving from across the Mediterranean, and the concrete that formed its bones absorbed the full weight of that traffic, the pressure of loaded hulls against its flanks, the constant pull and push of tidal water, for centuries before the harbour itself was eventually silted up and fell out of use. Even abandoned, the concrete remained. Far down the eastern coast of the Mediterranean, at the site of the ancient city of Caesarea Maritima, built by Herod the Great along the shore of what is now Israel, the same picture holds. The harbour there was one of the largest artificial ports in the ancient world at the time of its construction, a vast arrangement of breakwaters extending out into open sea, built from the same volcanic material mixed with lime and seawater. The sea has since reclaimed much of what was built above the waterline. Earthquakes shifted the coastline. The land subsided over the centuries, and much of what once stood above the surface now rests on the seafloor. And yet the concrete itself, the substance of those enormous underwater foundations and submerged walls, has not deteriorated in the way that the structures built above it have crumbled. The form has changed, has been broken by geological forces, but the material has held. There is a quiet strangeness in this, and it becomes stranger when placed beside what happens to marine concrete today. Modern concrete used in harbour construction is an engineered material designed with a precise understanding of chemistry, tested under controlled conditions, manufactured to consistent standards that the ancient world had no means to achieve. It is reinforced with steel to give it tensile strength, which is to say, the kind of strength that resists being pulled apart rather than simply compressed. Its proportions are calibrated, its curing is managed. And in seawater, it typically begins to show serious deterioration within a few decades. 50 years is a reasonable working life for many marine concrete structures. 100 years represents a long service in harsh saltwater conditions. The salt penetrates, the steel inside corrodes and expands, and as it expands it presses against the concrete from within, generating cracks that allow more water to enter, which corrodes more steel, which opens more cracks, until the structure has degraded beyond the point of repair and must be replaced entirely. This is not a failure of engineering in any careless sense. It is the behavior of a material that, however sophisticated, does not respond well to the particular chemistry of prolonged saltwater exposure. And so the harbors of the modern world require maintenance, inspection, reinforcement, and eventually replacement at intervals that would have been unrecognizable to the builders at Portus, who poured their material into the sea and left it there, and whose work the sea has been keeping ever since. The question of why this is the case, why ancient harbour concrete and modern harbour concrete behave so differently over time, sat unanswered for a very long time. For centuries, the answer that felt most natural was simply that the Romans had been exceptionally careful, that they had used good materials in good proportions and built with a seriousness of purpose that accounted for their durability. This was not an unreasonable conclusion. It was also, as it turned out, incomplete in a way that pointed towards something altogether more surprising, something that had been happening slowly and silently inside the concrete itself for longer than most civilizations have existed. The material itself begins the story in a particular place, a stretch of coastline near what is now the city of Pozzuoli, just west of Naples, where the ground has always been geologically restless, and the ash from ancient volcanic activity lies thick in the soil and along the shore. This ash, grey and fine, and unlike ordinary sand in ways that matter enormously, was the first essential ingredient in what Roman builders eventually came to rely on for work done in or near the sea. It is called pozzolanic ash, named for that region, and its particular chemistry. The way its silica and alumina compounds behave when mixed with lime and water is what separates Roman marine concrete from most of what came before and much of what came after. The lime was the second ingredient, and it arrived at the mixture through burning, the way lime always does. Limestone or seashells heated to high temperatures break down into a reactive powder that, when combined with water, releases heat and begins to change again, reaching toward new chemical arrangements. It is a material that has a kind of urgency to it in its raw state, a tendency to react, to combine, to settle into something harder and more stable than it began. The Romans had worked with lime in construction for generations, in walls and floors and cisterns, and they understood its behavior in the way that people understand materials they have handled across long spans of accumulated time, not through formal study, but through the slow education of observation and repetition. The seawater was the third ingredient, and this is perhaps the detail that most consistently surprises people encountering the mixture for the first time. The concrete was not protected from the sea during its construction, it was mixed with it. Seawater was introduced deliberately into the mixture, combined with the ash and lime into a dense, heavy paste that was then poured directly into wooden forms set into the harbour or lowered in containers beneath the surface where it would cure in the very environment it was built to withstand. The presence of salt and the particular mineral content of Mediterranean seawater, far from being contaminants to be avoided, were part of what the material was designed to meet. What happens chemically when pozzolanic ash, lime and seawater are brought together is a process of gradual crystallization, the slow formation of mineral structures within the mixture as it sets. The lime and ash react over time, producing interlocking crystals that bind the aggregate, the chunks of rock and broken rubble packed into the mass, into a solid whole. The process is not fast. Modern concrete made with ordinary Portland cement, the grey material used in nearly all contemporary construction, reaches most of its working strength within a matter of days or weeks. Roman marine concrete continued to strengthen over years and even decades as its internal crystalline structures continued to develop, the material slowly becoming more itself the longer it was left undisturbed. The Romans did not arrive at this formula through calculation. There were no laboratories, no controlled experiments, no written theory of materials, science guiding the proportions of each ingredient. What existed instead was accumulated craft knowledge, passed through generations of builders who had worked along this coastline long enough to notice which materials held and which did not, which mixtures cracked under the pressure of tides, and which seemed to grow only more solid with time. The volcanic ash from the Pozzuoli region had been used in construction for centuries before the great harbour projects, and its particular usefulness in wet conditions had been observed and remembered and passed forward in the way that practical knowledge travels, through demonstration and repetition rather than documentation. There is something in the texture of this knowledge that is worth pausing on, the way it is embodied in the act of mixing rather than recorded in a formula. A builder who has handled pozzolanic ash many times knows how it behaves differently from ordinary sand under the hands. how it accepts water differently, how the mixture shifts in consistency as the lime is introduced. The weight of the aggregate as it is packed into the forms, the resistance of the paste, the particular smell of the lime reacting in the open air. These are not details that appear in any surviving text, but they were certainly part of the knowledge carried in the hands and memories of the people who built the harbour walls at Portus and Caesarea, and the dozens of other Roman ports whose traces remain visible along the Mediterranean coast. The forms themselves were typically wooden, temporary structures set into position along the harbour edge or floated out to where the breakwater would stand. The mixture was poured in sections, each layer allowed to begin setting before the next was added, the whole assemblage slowly consolidating into a single mass. Below the waterline, the curing took place in the presence of the sea, the salt water moving through the still soft material as it hardened, becoming part of the matrix rather than an intrusion into it. When the wooden forms were eventually removed, what remained was already a unit with the water, not resistant to it in the way of a sealed surface, but continuous with it in a way that would prove, over the very long term, to be something closer to a collaboration. The piers and breakwaters that resulted from this process were not light structures. They were massive, heavy things, built with the understanding that what stands in the sea must be capable of absorbing force without transferring it into fracture. Their weight was part of their function, pressing down into the harbour floor, resisting the lateral push of waves through sheer presence. And within that mass, scattered through the grey and dark aggregate like pale interruptions, were small white chunks that had not fully dissolved into the surrounding material during mixing. Irregular, softer than the rest, present in nearly every sample ever taken from a Roman marine concrete structure. For a long time, these small white inclusions were read as evidence of imperfect work, lime that had not been thoroughly integrated, a minor flaw in an otherwise impressive material. The story of what they actually are and what they have been quietly doing for 2,000 years belongs to a later part of the night. The simpler explanation had a long and comfortable life. For centuries, the working assumption about Roman marine concrete rested on something close to admiration, the kind that looks at an old and sturdy thing and concludes that it must have been made by people who knew exactly what they were doing, who took their time, who did not cut corners. And this was not an unreasonable place to land. The structures themselves seemed to argue for it. Stand at the edge of what remains at Caesarea, or trace the submerged outline of a pier at Portus, and the material communicates something. A density, a settled weight, the quality of something that was built to last and simply has. The inference felt almost inevitable. Here was concrete made right, made carefully, made with the best available ingredients in the best available proportions, and its endurance was the straightforward consequence of that initial quality. This was the picture that persisted through most of the serious study of Roman construction materials. It was not careless or uninformed. Researchers had examined the ingredients, had understood that the volcanic ash from the region around Pozzuoli was unusually reactive, had noted that the lime and seawater combination produced a material with a particular internal structure. The chemistry of the initial setting process had been traced in reasonable detail. And when the resulting material was compared to its modern equivalents, the conclusion was that the Romans had, through long accumulated practice, arrived at a formula that produced an exceptionally stable product. The stability, in this telling, was the product of a kind of excellence concentrated at a single point in time, the moment of mixing, the moment of placement, the slow weeks and months of curing in the harbour water. Everything important happened then. What followed was simply duration. There is something appealing about that framing, and something quietly incomplete about it. It treats the concrete as a finished thing from the moment it hardened, a static object moving through time, wearing down by degrees its remaining strength, the balance left over from what was originally deposited. In this view, 2,000 years of survival means 2,000 years of very slow loss, a long subtraction that has not yet reached zero. The material is impressive because it started from a high enough point that even centuries of tidal exposure and salt and pressure and the slow chemical aggression of the sea have not been enough to exhaust it. That picture sat comfortably in the literature for a long time because it was largely consistent with what observation could confirm. The structures were still standing. The material was still hard. Under analysis, the internal matrix of the concrete looked dense and well integrated, the volcanic ash and lime having reacted together into interlocking mineral formations that were genuinely difficult for water to disrupt. All of this was real. All of this contributed to the longevity of the material. The assumption that it fully explained the longevity was the part that would eventually come loose. What the assumption missed was the possibility that the concrete was not simply holding, that something beyond passive resistance might be at work, that the material might not be finishing a slow decline from an impressive beginning, but might instead be doing something the researchers had not thought to look for, something so gradual and so distributed throughout the fabric of the structure that it would not announce itself under ordinary observation. The assumption of static endurance made it easy to overlook anything that looked like process, anything that suggested ongoing change rather than settled stability. The small white inclusions, those pale, irregular chunks that had been noted in samples and set aside as mixing imperfections, fit neatly into the assumption. If the concrete's strength came from the quality of its initial preparation, then the white chunks were simply evidence of where that preparation had been slightly less thorough. They were a minor blemish on an otherwise excellent material. They did not need to be understood more deeply because they were already explained. Incomplete mixing, lime that had not fully reacted, a small imperfection that the overall quality of the formula had easily absorbed. The assumption provided them a place, and in that place they sat, unremarkable, for longer than most institutions have managed to exist. What tends to happen with long-held assumptions is not that they collapse dramatically. They do not usually break open under the weight of a single contrary finding. More often, they soften at the edges first. A detail does not fit quite as neatly as it should. A measurement comes back slightly unexpected. Someone looks at a familiar thing from an unfamiliar angle and finds that the familiar explanation leaves something unaccounted for. The assumption about Roman concrete softened in exactly this way, gradually, as more refined tools made it possible to examine the material at smaller and smaller scales, to look not just at what it was made of, but at what was happening at the boundaries between its components, at the interfaces where one mineral met another, where water had moved through a hairline gap and left traces of its passage. At that scale, the picture of a static and slowly declining material began to look less complete. The traces water left behind were not always the traces of damage. Something else was happening in those narrow spaces, something that the assumption of fixed initial quality only durability had not predicted and could not easily absorb. The white inclusions, sitting in their assigned category of imperfection, were about to be reconsidered. The white inclusions themselves are easy to overlook when a sample is examined quickly or from a distance. They appear as small, pale shapes scattered without obvious pattern through the darker body of the concrete, irregular in outline, chalky in color against the warm gray and brown tones of the surrounding volcanic ash and aggregate. Some are no larger than a grain of rice. Others reach several millimeters across. In cross-section, when a sample is cut and polished and laid under magnification, they catch the light differently from everything around them, brighter, with a quality that is almost luminous against the denser matrix they inhabit. For a long time, the professional judgment that settled around them was fairly simple. Lime, in the making of ancient concrete, needed to be slaked. That is, burned limestone had to be mixed thoroughly with water before it could be incorporated into the final mixture, transforming it into a workable paste. If that process was rushed, or if pieces of the original limestone were not fully converted, or if the mixing was uneven, then small pockets of insufficiently processed lime could end up locked into the finished material, preserved there as the rest of the concrete hardened around them. The white inclusions seemed to fit this explanation perfectly. They were, in the language of materials science, inclusions, meaning fragments of something that had not fully become part of the intended final substance. The implication was slightly unflattering, at least to the idea of Roman workmanship as uniformly careful. It suggested that somewhere in the process, whether through haste at a large harbour construction site or through the inherent difficulty of managing large volumes of hot, reactive lime in the open air near the sea, some material had been incorporated before it was quite ready. The finished product still worked, still set, still proved durable, but the lime clasts were read as minor evidence of human imperfection, the small, careless notes in an otherwise careful composition. This reading was understandable. It matched what was visually apparent. The clasts did look like remnant material, something not fully digested by the process. And because they appeared to be inert, locked in place, not reacting, simply sitting there as the concrete around them aged, there was no particular reason to investigate them further. They were accounted for. They had a category. The category was flaw. What made that category so persistent for so long was partly that it required nothing more. The concrete was already impressive enough without its white flecks needing an explanation more interesting than incomplete mixing. The overall performance of Roman marine concrete could be attributed to the quality of the volcanic ash, to the particular chemistry of the lime and seawater combination, to the care taken in formulation and placement. The lime clasts were a footnote, and the footnote seemed closed. But samples of Roman concrete are not abundant in the way that other ancient materials are. Extracting cores from a harbour structure that has survived 2,000 years involves a kind of reluctance, a measured weighing of the value of knowledge against the cost of intrusion into something irreplaceable. The samples that had been taken and studied were studied carefully, and as analytical tools became more precise, as the instruments available to researchers allowed them to distinguish not just what minerals were present, but how those minerals were arranged, what their internal structure looked like, what had crystallized where and when. The lime clasts began to yield information that their outward appearance had not suggested. The pale, chalky surface was not the whole story. Inside many of the clasts, at their edges where the clast met the surrounding volcanic ash matrix, there were signs of chemistry. Not old chemistry, not the original chemistry of mixing, but something ongoing, or at least something that had continued long after the concrete was placed and set. The boundaries between the clasts and the material around them were not clean, frozen lines. They were zones of gradual transition, places where minerals from one phase had moved into another, where new crystalline structures had grown that belonged to neither the original lime nor the original ash, but to some combination of the two, a combination that could only have formed in the presence of water over time, long after the concrete was made. This was the detail that didn't fit the existing picture. A flaw preserved by hardening should be inert, a bubble, a void, an incorporated particle that didn't fully react. These things would simply sit there, doing nothing, until some external force disturbed them. The lime clasts were not sitting there doing nothing. They were, or had been, doing something. At their edges, at the boundary where they touched everything else, there was evidence of a process that had continued quietly, in the dark interior of the concrete, with no one watching. The question of what that process was, and what it had been doing to the concrete around the clasts over all those centuries, would require a different kind of attention than the samples had previously received. It would require looking not at what the clasts were made of, but at what happened to them when water moved through. And water, in a marine structure sitting at the edge of the sea, was never absent. It was always there, always moving, always finding its way through the smallest available pathways. the hairline cracks that form in any solid material as it ages and shifts and responds to the slow pressure of tides. The answer, when it came, was not complicated in its outline, though it was precise and specific in its chemistry. It had been present in the concrete all along, built into the material at the moment it was mixed, waiting in the form of those small pale shapes that had been mistaken for evidence of inattention. What looked like the trace of a shortcut turned out to be something closer to a mechanism, not designed, not intentional in the way a modern engineered solution would be intentional, but real and effective and still working. The seawater moves through the crack the way water always moves, without urgency, without direction, simply following the available space until there is no more space to follow. The crack is barely a crack in any visible sense. It is more like a parting, a place where the internal structure of the concrete has shifted by a distance so small it has no name in ordinary language. But water finds it, and water enters. And what happens next is the part that took so long to understand. When the seawater reaches a limeclast, one of those small pale irregularities sitting embedded in the surrounding mass, it begins to dissolve it. Not quickly, not in any way that could be observed in a single tide or a single season or even a single decade. The dissolution happens at the pace of the material itself, which is to say, at a pace that belongs more to geology than to ordinary experience. But it happens. The lime, which had sat unchanged since the harbour wall was first built, begins to come apart at its outer surface, releasing minerals into the thin film of seawater pressing against it from all sides. Those minerals do not stay dissolved for long. The chemistry of the seawater, the temperature of the surrounding stone, the pressure of the enclosing material, all of these conditions work together to make the dissolved minerals unstable in their dissolved form. They want to become solid again, and they do. They recrystallize, and they do so not in some open space away from the crack, but inside the crack itself, in the precise location where the seawater brought them. The mineral growth fills the space. It reinforces the walls of the crack from within, and when the process is complete, which may take years or decades, the crack is no longer a crack in any meaningful structural sense. The concrete is, in that place, whole again. The mineral that grows in the crack is calcium carbonate, a dense crystalline solid that bonds tightly to the surrounding concrete. It is the same family of mineral that makes the original Roman mixture so hard in the first place, and its growth inside the crack is not incidental. It genuinely strengthens the repaired area. The seawater has not simply deposited something into a gap. It has facilitated the growth of new structural material in a place where structural material had begun to fail. This is what the 2023 study, led by researchers at the Massachusetts Institute of Technology alongside colleagues from Harvard University and institutions in Italy and Switzerland, was able to document with enough precision to close the question. The limeclasts were not oversights. They were not the residue of insufficient care. They were, in effect, the latent capacity of the concrete to respond to damage, not designed as such by the Romans, who had no vocabulary for what they were doing at that level of detail, but present nonetheless, built in through the accumulated logic of a recipe that had been refined over generations of practice at the water's edge. The contrast with modern marine concrete is not dramatic in its telling, but it is significant in its outcome. The concrete mixtures used most widely in contemporary harbour construction are designed to resist water entry from the beginning. They are dense, their internal structure is tight, and the assumption behind them is that keeping water out is the goal. When water does enter, as it eventually does, because no marine structure remains perfectly sealed against the sea across any significant span of time, the results tend to accelerate. Water works into the interior, reaches the steel reinforcing bars embedded in most modern concrete, and begins to corrode them. As the steel corrodes, it expands, and the expansion cracks the concrete further, which allows more water in, which accelerates the corrosion. The process is self-reinforcing in the wrong direction. The intrusion of water does not heal the structure. It unmakes it incrementally but reliably, and the timeline is often measured in decades rather than centuries. Roman marine concrete had no steel reinforcement to corrode. It had no dense sealed matrix to be breached in ways that could not be recovered. What it had instead was a porous, mineralogically active interior that did not resist water so much as incorporate it, and lime clasts distributed through the mass that could respond to the presence of water by releasing material capable of filling the damage water had caused. The water was not the enemy of the structure. The water was, in a slow and indirect sense, part of how the structure maintained itself. There is something worth sitting with in the specificity of this. The seawater had to be seawater. It carries a particular mineral chemistry that fresh water does not, and the reactions that take place at the lime-classed surface depend on what the water brings with it. The volcanic ash had to be from the particular region around the Bay of Naples, a geological material with a silica content and a mineral composition that made it reactive in ways that ordinary stone aggregate was not. The lime had to be present in clasts rather than fully dissolved into the mix, which meant the preparation technique that produced incomplete mixing was not a failure of the process, but an output of it. All of these things had to be true at the same time, in the same material, for the self-repair mechanism to exist. The Romans did not know they had assembled all the necessary conditions, but they had, and the sea has been slowly confirming it ever since. The confirmation has arrived in quiet increments, across a span of time that resists ordinary comprehension. It helps, sometimes, to place it against something familiar. The Roman harbour at Caesarea Maritima was already old when the first medieval cathedrals of Europe began to rise. Those cathedrals themselves are now ancient, their stones worn smooth by centuries of weather and human hands. And through all of it, through the building and falling of empires, through the slow disappearance of the language in which the structures were commissioned, through every transformation of the coastline and the culture, and the very idea of what a harbour is for, the concrete has been doing its small, invisible work. A hairline crack forms. Seawater finds it. Minerals dissolve and recrystallize. The crack closes. No one observes this. No one needs to. The process requires nothing from the outside world except the seawater that is already there, pressing in as it always has, patient and indifferent, and, in this particular case, quietly useful. There is something unusual about the scale of this. Most processes that operate across 2,000 years leave some visible record of their passage. Rock erodes, and the erosion accumulates into new landforms. Ice advances and retreats, and the landscape carries the marks of where it has been. Even the slow drift of tectonic plates, which moves at roughly the speed at which a fingernail grows, eventually opens oceans and raises mountain ranges. But the self-repair happening inside these harbour walls leaves almost no trace of itself. It does not accumulate visibly. It does not leave a record that can be read from the outside. It simply maintains, holds the line, keeps the structure from becoming something other than what it is. The harbour walls at Portus look, from the surface, much as they have always looked. What is happening inside them is invisible at any human scale of attention. This is the kind of process that only becomes legible in retrospect, and only then if the right questions are being asked. For generations, researchers looked at these structures and saw endurance. They saw duration. They asked, reasonably, what the Romans had done so well at the beginning, and they looked for answers in the initial quality of the materials, the care of the mixing, the favorable chemistry of the volcanic ash. All of those things are real, and all of them matter. But they were looking for a completed action, something done once and lasting. The actual mechanism is not completed. It is ongoing. The concrete is not a record of past craftsmanship, so much as it is an active, continuing process that happens to be legible as a structure from a sufficient distance. The pace of it is worth dwelling on. Each individual repair event, each small crystal forming inside a small crack, would take place across months or years. The crack that forms in a harbor pier is not dramatic. It is the kind of fracture that develops under the ordinary, accumulated pressure of thermal cycling, of tidal movement, of the slow settling of material over long periods. It is too small to cause concern, and too small to observe without instruments. The water that finds it moves slowly, seeping through pores at a pace that has no analogue in ordinary human experience of water moving. And the crystallization that follows is slower still, mineral matter reorganizing itself from solution into solid form in the dark interior of the concrete, in a gap that might be a fraction of a millimeter wide. This is not something that anyone has ever watched happen in real time. It is something reconstructed from careful study of the material itself, from the chemistry of what is found where, from the shapes of crystals growing in spaces that were once empty. And yet, the cumulative effect of all these slow, invisible, individual events is the thing that is now visible from a boat in the Mediterranean, or from the edge of a harbor where the water is clear enough to see the ancient stone structure still holding its shape below the surface. The cumulative effect is 2,000 years of presence. The cumulative effect is a breakwater that is still breaking waves that roll in from open water, still sheltering whatever is behind it, still doing the thing it was built to do, for reasons that no one fully understood until very recently. There is a certain kind of institution that keeps careful records of its own continuity. Libraries catalogue their holdings across centuries. Religious orders track the generations of their members. Dynasties maintain genealogies that link the present to a distant founding moment. But the harbor walls do not track anything. They do not maintain any record of their own persistence. They simply persist, repairing themselves in the dark and the cold and the salt, entirely without intention, responding to the chemistry around them with a process so fundamental that it requires no oversight and no understanding to function. The Romans who poured the mixture into the wooden forms, who watched it settle into the Mediterranean and harden against the pressure of the incoming tide, were thinking about ships and commerce and the reach of the empire across the sea. They were thinking in the scale of years, perhaps of decades, imagining the harbor as it would look when finished, imagining the vessels that would shelter inside it, imagining the goods that would move through it. They were not thinking about crystals forming in microscopic cracks 200 years in the future, or 800 years, or 2000. That thought was not available to them. The knowledge was not there. But the mechanism was, locked into the material by the accumulated practical knowledge of generations of builders who had learned, without understanding why, that this particular combination of materials behaved differently from others when it met the sea. What was built in a moment of human time has been repairing itself across a span of time that contains, within it, the entire subsequent history of the civilization that built it. And now, in the present, people are studying that material again, not to understand history, but to understand chemistry, and through that, to understand what it might be possible to build next. Research teams have taken core samples from the surviving harbor structures at Portus and Caesarea Maritima, and from other Roman sites where seawater has been the constant companion of the concrete for just as long. The samples are cut and polished and examined at scales far too small to see with the naked eye, using instruments that can trace the path of individual minerals through a cross-section of stone, measuring their composition and density and the particular way they are arranged. What those instruments show is not the slow degradation that was long assumed to be accumulating invisibly inside the material. What they show is a kind of internal order, evidence of repeated cycles of fracture and healing, of seawater moving through and leaving behind the mineral deposits that closed the paths it had opened. That evidence is the basis for what engineers and materials researchers are now trying to do. The project is essentially one of translation, taking a process that occurred without any deliberate design, that was never understood by the people who first set it in motion, and finding a way to reproduce it in materials that can be specified, manufactured, and placed in the harbors and seawalls and coastal infrastructure that will be needed in the coming decades and centuries. It is, in that sense, a reversal of the usual relationship between the ancient and the modern, where new knowledge replaces old methods. Here the knowledge is new, but what it points toward is old. The translation is not straightforward. The volcanic ash that was central to the original Roman mixture is not uniformly available everywhere in the world. The particular chemistry that made the combination work, the way the ash and the lime interacted to produce a material that remained slightly reactive even after it hardened, is difficult to replicate using more widely available materials. But the principle that underlies it is now understood clearly enough that researchers have something real to work with. They are not trying to reproduce a recipe. They are trying to reproduce a behavior, and those are different problems, one of which has proven much more tractable than the other. There is something in that distinction that carries a quiet kind of meaning. The Roman builders never knew the recipe in the sense of understanding why it worked. They knew what to combine, and in what proportions, because those proportions had been arrived at through long practice and careful observation, passed down through generations of people who built in the same places with the same materials. The knowledge was embedded in the tradition rather than in any formal understanding of what the materials were doing. What modern researchers have now is the formal understanding, a precise account of the mechanism, the chemistry, the crystalline structures that form inside the cracks. What they are working to recover is the outcome the practice had already found. The destination is the same. The path there runs in the opposite direction. The pace of that work is unhurried, in the way that all genuinely foundational research tends to be. There are no harbors yet built on the principle of the limeclast. There are no seawalls currently healing themselves through a mechanism derived from the study of Roman marine concrete. That phase is still approaching, somewhere ahead in the ordinary unspooling of scientific and engineering work, in the testing of materials and the refinement of formulas and the slow accumulation of field results from structures that have been in the water long enough to show what they are actually doing. Meanwhile, the original structures continue to stand in the sea. The harbor at Caesarea Maritima is largely submerged, visible from above in clear water, the outline of the ancient breakwaters still legible in the shape of the seafloor. At Portus, the remains of the Great Basin are present in the land itself, transformed over centuries by silt and time into a form that is no longer exactly a harbor, but is still recognizably the shape of one. The material that holds those forms together is still doing what it has always done, meeting the water, wherever water reaches it, with the same slow chemistry that has been operating since the structures were new. There is no obvious moment at which that process will stop. The concrete is not spending down toward an endpoint in the way that was once assumed. It is, within the limits of what can be measured and observed, sustaining itself. The cracks that form are the cracks that close. The water that enters is the water that brings the minerals to fill the space it has made. The process does not require attention or care or any human intervention at all. It requires only time and seawater and the particular combination of materials that was arrived at without any formal knowledge of what it was doing by people working at the edge of the Mediterranean 2,000 years ago. That is where the story settles. Not in a discovery or a resolution or anything that announces itself as an ending. It settles in the image of water moving through stone, minerals dissolving and recrystallizing in the dark, a harbor wall standing in the sea on a morning when no one is watching, the surface of the water flat and pale and very still,